Alright guys, first off, welcome back to another video, and also welcome back to a brand new series. So today we are going to be doing something a little bit different. Today we are going to save some monkeys. Yep, that's right. Today we are going to save some monkeys, and we're going to do it using calculus. Okay, so if you've taken a high school physics course, then you've probably heard of the classic monkey hunter problem. Basically, you have a monkey hanging from a tree branch, minding his own business, and then along comes a hunter. The hunter, he sees the monkey, gets in position, then aims an arrow directly at the center of the monkey. But our monkey, he's a clever little guy, and he sees what's going on, so he devises a plan. As soon as the hunter releases the arrow, the monkey is going to let go from his tree branch to dodge the arrow, then fall safely to the ground. That is the monkey's grand plan, but the question is, will it work? Will the monkey successfully dodge the arrow and survive, or despite his efforts, will he be shot and killed? Well, before we can even answer that question, we need to look at the kinematics. So first of all, when the monkey lets go of his tree branch, he's only going to fall in the vertical direction. So his x-coordinate as a function of time will remain constant at x equals L. Additionally, we will assume that the only force acting on the monkey is the force of gravity. So using this free body diagram, we can evaluate Newton's law in the y direction, cancel the m's, integrate once, integrate twice, then apply the initial conditions. So remember, the monkey's y-coordinate starts at a height h, and his velocity starts from rest. So we can apply these initial conditions, and what we get is the y-coordinate of the monkey as a function of time. So together, these two equations define the kinematics for the monkey. Alright, so let's go ahead and do the same thing, but this time for the projectile that the hunter shoots. Here we have the free body diagram for the projectile. First, we will use this to evaluate Newton's law in the y direction, cancel the m's, integrate once, integrate twice, and now we have the general solution. So recall, the projectile is fired at a velocity v from the origin, so its initial y-coordinate is 0, and its initial y velocity is v times sine theta. So when we apply these initial conditions, we get the y-coordinate of the projectile as a function of time. Now let's use our free body diagram to evaluate Newton's law in the x direction. So we can cancel the m, integrate once, integrate twice, then apply the initial conditions for the x direction. And so what we get is the x-coordinate of the projectile as a function of time. So together, these two equations define the kinematics for the projectile. And combining the results, we have the kinematics for the monkey-hunter problem. To determine whether or not the monkey will survive, we are going to run some simulations. Remember, as soon as the hunter pulls the trigger, the monkey is going to let go from his branch in an attempt to avoid the arrow. So let's see what happens. Well, turns out the monkey isn't so lucky. And actually, you may be surprised to find out it doesn't even matter how fast the hunter shoots the arrow. He can fire 10 different arrows at 10 different speeds, and no matter what, each arrow will hit the monkey in precisely the same spot. So no matter what, the monkey always dies. Okay, before we try to save these monkeys from their inevitable death, let's break down the math so that we can understand what we just saw. When the hunter fires the projectile, it doesn't reach the monkey until their x-coordinates are equal to each other. When this happens, we can substitute in our kinematic equations that we previously derived, then solve for the time that it takes for the projectile to reach the monkey, which we will call t star. Then, if we evaluate the y-coordinates of the projectile and the monkey at t star, and simplify, then what we see is that the y-coordinates are also equal. So what this means is that no matter how far the hunter is from the monkey, or how high up in the tree the monkey is, or even how fast the projectile is fired, after the projectile travels for t-star seconds, it will hit the monkey and the monkey will die. Now, I know what you're thinking. How can physics be so cruel, with probably thousands of hypothetical monkeys dying every semester in physics class? Well, that's where we come in, because we are going to fix this tragedy. We are going to save these poor innocent monkeys with one little tweak. And that is, we are going to consider air resistance by including drag forces in our analysis. So before, we only considered forces from gravity. Now we are going to throw in a drag force to model air resistance. So what is the drag force? Well, we will estimate the drag force using the standard drag equation, which is proportional to an object's velocity squared. It also depends on the cross-sectional area, the density of air, or the fluid that it's moving through, and also something called the drag coefficient, which is largely dependent on the object's geometry. So with that in mind, let's go ahead and rederive the kinematics for the monkey, but this time including the drag force, which gives us an additional term when we evaluate Newton's law in the y direction. Okay, so first off, I'm going to define this quantity as k to make the notation look a little bit neater. So let's rewrite the equation, and now we can divide through by mg, clean up the notation again with a new variable beta, then separate and integrate. So the left integral we can do no problem. The right integral, let's go ahead and do a u substitution. Let's let u equal beta times vy, rewrite the integral, factor the denominator, then use partial fractions to break it up over the factors. Rewrite it as two separate integrals, integrate easily, then simplify using the properties of logarithms. Now let's multiply both sides by 2 beta and take the exponential of both sides. Then we can apply our initial conditions. So remember, u equals beta times vy, which makes u of 0 equal to 0 since the monkey starts from rest. And that gives us c is equal to 1. So we can just get rid of the c right here. Now we can rearrange to solve for u, substitute back in for u, then rewrite vy as dy dt. Next, let's separate and integrate. The integral of dy is just y, easy enough. So let's just work with this left integral over here. First, we split it up over the denominator, simplify the first fraction, then rewrite it as 2 separate integrals. Okay, so next let's add a smart 0 to the numerators, split it up over the denominator and simplify once more, and then we can cancel the 1's. Now we can introduce a change of variables z for the first integral and w for the second, which lets us simplify the integral to something very easy to work with. So let's go ahead and integrate, simplify using properties of logarithms, then substitute back in for z and w. Okay, so we've got the general solution for y. So recall, the monkey starts up in the tree at an initial height of h. So we can solve for c, throw it back into the equation, and then substitute back in for beta. So here we go, the final expression for the y-coordinate of the monkey. But we aren't done yet because we still need to define the drag constant k. But before we can even evaluate k, we need to figure out what type of monkeys we are hunting. And I don't know about you guys, but I'm feeling like hunting some chimpanzees today. Alright, so I did a little research. The average chimp is about 3.8 feet tall and weighs 50 kilograms. So they're going to be pretty chubby and round, so we can treat the cross-section of their bodies like a circle with a diameter of half their height. That's probably a safe estimate. Anyway, for the drag coefficient, we're going to estimate it as being equal to that of a human falling through the air in a vertical position. Luckily, we can use the results from a study published online where they actually experimentally determined this to be approximately 0.2 using a wind tunnel. And then finally, of course, we'll use the density of air at standard temperature for rho, which gives us 0.032 for k. And combining results, we have a complete description of the kinematics for the monkey with air drag included. Here we have 2 monkeys. The gray one will experience drag and the brown one will not. And using the equations we just derived, we can simulate how they fall. but if we compare their positions just before they hit the ground, we see that the difference in their y coordinates only differs by less than 2 centimeters, which is actually pretty much negligible. But then again, every centimeter counts, so we'll just keep this in the back of our minds. Okay, let's move on to the projectile. So previously we only considered the force of gravity, and now we're going to throw on a drag force. Since drag always points opposite to the velocity vector, we'll draw it like this. Using the drag equation, we can rewrite the drag force and then clean up the notation using a new variable k. Now we'll split up the drag force up into x and y components and apply Newton's law for both directions. Evaluating and simplifying gives us the following result, which unfortunately does not have an analytic solution. So to get around this, we're going to apply a low angle approximation. That is, we're going to assume that the hunter isn't pointing his weapon too high, and so the square of the ratio of the y to x components of the projectile's velocity will be small enough to neglect. So we can actually use this to simplify our system of differential equations like this. Okay, so we have two differential equations that can now be solved analytically, but notice they're still coupled, so we'll have to solve the x direction first. Let's go ahead and rearrange and integrate. Then we can take the reciprocal of both sides to get the general solution. Now recall the initial x velocity is going to be the firing velocity v times cosine theta, so we can apply the initial condition to get the x velocity component as a function of time. Now let's rewrite the x velocity as dx dt, separate and integrate. And since the projectile starts at the origin, we set the initial condition to 0, then use that to get the unique solution, which we can then rewrite in terms of L and H using this triangle. Now onto the y component. Let's divide by m, substitute in our result for Vx, and then rearrange. Clean up some notation by introducing a new variable alpha, and then rearrange. So what we have here is a first order, non-separable linear differential equation. If you don't know how to solve this, I'll drop a video card right here so you can check it out later. But anyway, all we need to do is define an integrating factor. Multiply through both sides of the equation by this factor, and then simplify. Now we can easily integrate both sides. The left side, we just undo the product rule, and the right side, well, that's just straightforward. So that lets us solve for Vy. Now recall, the y component of velocity starts at the firing velocity times sine theta, so we can apply that initial condition, solve for c, then rewrite Vy as dy dt. Next, we separate and integrate both sides. The integral of dy is just y, so that's easy. The third integral on the right side can easily be evaluated using natural log, and the first integral can be simplified and rewritten. Now the first integral is easy, so we can just do that, then regroup some things and rewrite, and so all we have left to evaluate is the last integral. Let's go ahead and do a u substitution, and so using the definition of u, we can derive an expression for t squared in terms of u. So we can rewrite the integral in terms of u, split it up over the denominator, easily integrate, then substitute back in for u, then throw the whole thing back into our expression for y of t. Now let's go ahead and simplify, apply the initial condition of 0 since the projectile starts at the origin, and then we'll use that to get a unique solution. But can't forget to plug back in for alpha. Then use our triangle again to rewrite theta in terms of L and H. And there we have it. The y coordinate of the projectile is a function of time. But we still aren't done yet. We still need to evaluate k, just like we did for the monkey. So for the projectile, as we did in the case without drag, we will be using an arrow. A standard carbon hunting arrow has a mass of 20 grams and a shaft diameter of 6.5 millimeters. So we can use that for the diameter of the cross-sectional area. For the drag coefficient, we will reference a study which experimentally determined the drag coefficient of a standard carbon arrow to be approximately 1.94. And then for rho, we will of course use the density of air. So using these values, k comes out to be 0.00004. And together, we have the complete kinematics of the projectile with air drag included. And combining these results with the previous results for the monkey, we have the kinematics of the monkey-hunter problem with air drag. So let's go ahead and simulate these equations and see what happens. Alright, so we're back in the field, this time with air drag. Since the hunter is using arrows, we are going to place him at 30 meters away from the monkey so that he is within the effective range of his bow. Now, before we can move on, we have to check that our small angle approximation is satisfied. Otherwise, the equations we just derived won't be valid. So when L equals 30 and H equals 6, tangent theta squared is less than 0.05, which is small enough to be neglected. So we are indeed firing at a low angle, and therefore our equations of motion are valid. So now let's go ahead and fire the first shot. Ooh, right in the face. Okay, well, that's not good. The monkey still died. It's almost as if the drag did not have any effect whatsoever. Even if we shoot a bunch of different arrows at different speeds, we see that the monkey still dies every single time. But we can go ahead and compare these trajectories to the arrows with no drag and observe that there is in fact some difference. But either way, the monkey still dies. But don't lose hope yet, because what this really means is that the hunter needs to move further from the tree. If he is much further than 30 meters from the tree, this will allow for the drag effects to accumulate to the point where the projectile misses the monkey. But it also means that he can no longer shoot arrows because he'll be outside the effective range of his bow or his crossbow. So instead, the obvious choice will be for the hunter to use an AR-15, which is capable of firing a 5.56mm bullet weighing 3.56 grams at a velocity of 988 meters per second. That's nearly 3 times the speed of sound. But of course, since we are now using a different projectile, we will need to reevaluate the drag constant K. So we'll go ahead and use the diameter of the bullet to calculate the circular cross-sectional area. For the drag coefficient, we will need to reference the G7 projectile curve, which is commonly used in ballistics for estimating drag coefficients for standard high-speed projectiles like bullets. Since the muzzle velocity is 988 meters per second and the speed of sound is 343 meters per second, we can calculate the Mach number, plot it on the drag curve, and then find the intersection value to determine the drag coefficient of the bullet, which comes out to be 0.25, so we'll go ahead and throw that into our expression for K. Then finally, we can plug in for the density of air to evaluate K for the bullet. So using these new values, we can combine them with the previous equations that we derived to redefine the kinematics for the monkey-hunter drag problem, but this time with bullets. So here we are, back in the simulation. This time the hunter is no longer shooting arrows at 30 meters, he is firing bullets at 600 meters. Which is around the maximum effective range of an AR-15. So this time, as soon as the monkey sees the muzzle flash, he will let go of his branch in an attempt to dodge the incoming bullet. So here we go. Wow, guys, I think we just saved this monkey. Let's go ahead and run that one more time. Okay, yeah, he may have clipped a nail or lost a finger, but I think he'll survive. Alright, for fun, let's go ahead and compare this to a bullet fired with no drag. Okay, so yeah, the bullet with no drag obviously hits the monkey, that's no surprise. But the bullet with drag, that comes a good solid 0.2 seconds afterwards. And so we can really see how the higher projectile velocity in the further range really allows for those drag effects to accumulate. But anyway, the point is we just saved this monkey using a more realistic ballistics model that we derived through a bunch of calculus. And it turns out it's not just this monkey that we can save a whole bunch of monkeys. But first we need to break down the math and see what's going on. When the bullet is fired, it doesn't actually reach the monkey until their x-coordinates are equal. So setting the x-coordinate of the bullet equal to the x-coordinate of the monkey, we can substitute in the previous derived expressions and solve for the time that it takes for the bullet to reach the monkey, which we will call t star. Now, in order for the monkey to survive, when the bullet reaches the monkey, it needs to pass overhead. And so for a monkey with a height of a, since the monkey's coordinate is measured from the center point where the hunter initially aims, we need the difference of those y coordinates of the bullet and the monkey to be greater than a over 2 in order for the monkey to successfully dodge the bullet. Substituting in our derived expressions, the following inequality must hold if the monkey is to survive. So for a monkey with a given height a, we can find the minimum distance that a hunter can be such that when he fires his AR-15 at the monkey, his bullet will miss, and the monkey will survive. So solving this inequality with the values that we previously determined, we get something that I will call the monkey survival chart. So all the monkeys above this curve, according to the inequality, are safe, and all of them below, may they rest in peace, are dead. But remember, the hunter will only attempt to shoot monkeys within the effective range of the AR-15, which are the monkeys below the 600-meter line right here. So actually, the only monkeys that we save from the hunter are the ones in this region right here. The others, they weren't so lucky. But more importantly, the blue star that you see right here, this represents the minimum safe distance for the average-sized chimpanzee. And what we see is that as long as the hunter is right around the maximum effective range of his AR, the monkey is safe, which is great because that means at that distance we can save the average monkey. Now, we can also see how well we did overall. If all these situations on this chart are equally likely, for example, if the hunter is equally likely to encounter a 3-foot tall monkey at 400 meters as he is to encounter a 4-foot monkey at 550 meters, then we can take the area of this safe zone over the total area of interest to get the percentage of monkeys that we actually saved, which in this case comes out to be 13.3%. So yeah, we just saved 13.3% of the monkeys that otherwise would have died under the classic monkey hunter problem. Okay, yeah, 13.3% may not seem like a big number, but when you consider the thousands of physics teachers that are killing hypothetical monkeys every semester in class, it actually comes out to be quite a few monkeys. So next time you see your physics teacher, be sure to tell him that with just a little extra calculus, it's not too late to save the monkey. Until next time.